Hello, welcome back. So we were discussing about forced oscillations where an external driving force is applied to sustain oscillations in a damped oscillator. Today let's discuss about the topic resonance. Resonance is a phenomenon where the amplitude of a forced oscillator becomes maximum. This occurs when the frequency of a periodically applied driving force is equal or close to the natural frequency of the system on which the driving force is acting. So, when we consider the forced oscillator, we consider that an external driving force F equal to F0 sin Pt is applied, where P is the angular frequency of the external driving force, which is oscillatory in nature. And if we plot the frequency of driving force along x-axis and the amplitude of the oscillator along y-axis, we can see that as the frequency of the driving force increases, the amplitude also increases, and finally it becomes a maximum and then decreases to a minimum. And this particular frequency at which the amplitude of the oscillator becomes maximum is called as the resonant frequency. Now, last time we saw that in case of a forced oscillator, the amplitude can be given by this expression where omega 0 is the natural frequency of the oscillator, P is the angular frequency of the external driving force, and C is or 2C equal to gamma by M, where gamma is the damping coefficient. We are following the equation numbers that we used last day, or continuing the equation numbers, and here we can see that this amplitude becomes maximum when this denominator is a minimum. That is, to obtain the condition for minimum of this denominator, we differentiate it, equating that to 0. We get this expression, and simplifying this expression, we get that when A is a maximum, P equals square root of omega 0 square minus 2C square. That is, at resonant frequency, that is when P equal to PR equal to root of omega 0 square minus 2C square, the amplitude of the forced oscillator is maximum. From this expression, it is clear that the resonant frequency PR is less than the natural frequency omega 0 since 2C square is subtracted from the omega 0 from this omega 0 square. Now, if you substitute this resonant frequency PR in the expression for this amplitude, we get the amplitude or the maximum amplitude at resonance. That means we are going to substitute this root of omega 0 square minus 2C square instead of P in this expression. We get the maximum amplitude or the amplitude of the forced oscillator at resonance equal to F0 divided by omega 0 square minus, instead of P square we substitute PR. Here also instead of P square we substitute PR, and then simplifying the denominator, please write it down, we get this expression. Finally, taking this 2C outside the root, we get F0 divided by 2C into square root of omega 0 square minus C square. Again, since PR equal to root of omega 0 square minus 2C square, we can rewrite this expression as F0 divided by 2C into root of PR square plus C square. Fine. This is the amplitude of the forced oscillator at resonance, or we can see that this is the maximum amplitude of the forced oscillator. Now, let's have some more discussion on the amplitude of this forced oscillator. It's clear that the amplitude of the forced oscillator depends on the difference between omega 0 and P. In this expression, we know that small f0 equal to f0 divided by m, where f0 is the amplitude of the external driving force and m is the mass of the oscillator. First, let us consider the case where p is much less than omega 0 square. From this expression, it is clear that when p is much less than omega 0 square, we can cancel this p square terms, then it is equal to f0 divided by omega 0 square. Again, we know that f0 equal to capital F0 by m and omega 0 square equal to k by m. Substituting those two, we get when p much less than omega 0 square, the amplitude of the driven or forced oscillator is equal to capital F0 by k, which indicates that this amplitude, when p is much less than omega 0, the amplitude of the forced oscillator does not depend on the mass of the oscillator, and also it does not depend on the damping. See, it's independent of the mass and it's independent of the damping present, and it depends only on the force constant of the oscillator. Again, as a second case, we consider when p equal to omega 0 square, that is when the natural frequency of the oscillator is equal to the frequency of the external driving force. In that case, we know that the amplitude becomes equal to f0 divided by square root of 4c square p square, which is equal to f0 by 2cp. Again, since p equal to omega 0, f0 divided by 2c omega 0 square. It's clear that this is less than the maximum amplitude. We can compare those two expressions. And again, when c is very small, or in case of small damping, we know that this amplitude becomes maximum. Then when this p is much greater than omega 0, that is when this p is much greater than omega 0 square, we can neglect this omega 0 square and this term also. Then the dominating term is f0 divided by square root of p raised to 4, that is at the amplitude when p is much greater than omega 0 square, the amplitude equal to f0 by p square. That depends on the mass, since small f0 is equal to capital F0 by m, that depends on the mass, and it decreases continuously with p, or it decreases continuously as the driving force is increased. These are the three special conditions of a forced harmonic oscillator. Now, you may be knowing that a group of soldiers, while marching on the bridge, are asked to break their steps very often. It's because if their synchronized footsteps resonate with the natural frequency of the bridge, it can collapse the bridge. We already know the case of Tacoma Bridge collapse, which happened due to this resonance. And here are some more examples of resonance from our daily life: at mass on a string at resonance, singing your leg in a swing, etc. And for further reading, you can refer to this interesting site. Thank you.